with Marcus Peinado talking about Hypervisor. Now, for those of you that recall, we've had discussions in the past about Inkscub and what it was designed, what the previous designs were like, and some of the technology discussions that revolved around that. We have made some changes and some engineering decisions that have resulted in some thinking about redesign. And Marcus is going to talk and give you a little bit of overview about the organizational changes, plus dive into Hypervisor from there. So with that, Marcus Peinado.
Thank you.
Oh, let me ditch. Yeah, sorry. Whoops. Slides would be nice. There you go.
Okay.
Here's a forward-back clicker if you want to.
Oh, okay.
Reverse, yeah.
Okay. Thank you. Good morning. This is the talk on the Microsoft Hypervisor. This is a new project designed to support NGSCB and other applications. I'll start out, before the real talk, I'll start out giving a little bit of context on what happened since we gave the last talk on NGSCB in last August. So if you recall, NGSCB, the way we've always presented it, consists essentially of two isolated operating systems running on a single machine. One important component of NGSCB was the component which would allow these two operating systems to run on a single machine and at the same time isolate them and protect them from each other. So we looked at this and the board also pointed out last year that this really looks very much like what in a more general sense a virtual machine monitor or a hypervisor does. So back in April, a decision was made for Microsoft to go ahead and start building a general purpose hypervisor, not just to support NGSCB, but to support a broader range of applications. So I think that's broadly in line with two of the main recommendations from the board last year. First one, to build a general purpose virtual machine monitor. And another recommendation, which you'll see reflected in the talk later on, was to exclude device management from the hypervisor itself. There have been a number of other changes to NGSCB, and I won't talk about them. They'll be discussed in the next talk. I'll limit myself to talking about the hypervisor. Another couple of general remarks about this talk. As I said, the work on the hypervisor started about 3.5 months ago. This is clearly work in progress. We're at a fairly early stage in the design process. That has, the disadvantage of this is that if you ask me detailed questions, I may not be able to answer all of them. On the other hand, this is a great time for us to receive feedback and actually take it into account, because it's a fairly early stage in the design process. And part of my motivation here is towards the end of the talk, I'll actually be asking for feedback in specific areas. Good. Those are the introductory remarks. Let's start with the actual talk. Here's an overview. I'll start out with trying to describe the problem that we're trying to solve in a general sense. That's sort of the motivation and goals section. The rest of the talk will really describe architectural and design aspects of the hypervisor, and I'll start out with sort of a high-level pass through it, and after that I'll go I'll look at some areas, the areas listed here at the bottom, and talk about them in a little more detail. Good. So let's start with the motivation and goals. Start out with some terminology just to make sure that I'm using well-defined terms here. By hypervisor, I mean something like a stripped-down virtual machine monitor, a layer of software that sits just above the hardware and beneath one or more operating systems that it hosts. Its primary purpose is to provide isolated execution environments for different kinds of software to run in. We use the term partition, which is essentially equivalent to what's sometimes called a virtual machine. It's multi-isolated execution environments that the hypervisor provides for software to run in, and the software that runs in these partitions I'll be referring to as guests. Just to be a little bit more concrete here. So what are typical guests and what are typical configurations of the systems? So a typical guest would be an operating system, and this may be an unmodified off-the-shelf operating system, or it may be a somewhat adapted operating system. In a typical configuration, the hypervisor exposes several virtual machines or several partitions and allows several operating systems to run in. So you might have one computer and run Windows in one virtual machine and some Unix version in another virtual machine. So it's essentially what virtual machine monitors do. The partition looks to a guest like a real physical machine. It comes with memory, one or more CPUs, interrupts, and at some point concrete devices such as a disk or a network card. Some related work. This list here is not exhaustive, but it's sort of just I'm just trying to give you an idea of the kind of things we've been looking at as we're designing the system. So on the one hand, there is this vast body of work on virtual machine monitors from mainframes from the 1970s, mostly coming out of IBM. Then another important body of work are sort of the Orange Book style systems. And the one we've been looking at most closely has been the SVS system that DEC was building in the 1980s, which was essentially a high assurance virtual machine monitor, pretty much what we're trying to build here as well. Other kinds of things people have been looking at more recently are small isolation kernels like the exokernel or the Nelly system out of University of Washington. And then, of course, there are the virtual machine monitors for personal computers people have been building more recently. The Xen system out of University of Cambridge, and of course, the commercial systems, Virtual PC and VMware. Good. So here's the problem we're trying to solve. Target use areas or scenarios. So first one, of course, NGSCB. And if you think of a configuration in which you have a hypervisor and which hosts two operating systems, one of them is Windows and another one is some sort of a high assurance secure operating system, then you pretty much end up with what NGSCB always used to be. But now there are more configurations we're trying to support. Another important application here is server consolidation. One of the main applications for virtual machine monitors these days. People move, instead of buying 3 physical machines or n physical machines, they buy one big machine and take a virtual machine monitor and run different kinds of web servers or other kinds of servers in isolated partitions. Another important application is legacy support. So whenever Microsoft releases a new operating system, one of the main problems or cost factors is trying to make all the applications which ran on the previous operating system, make them run on the new version of the operating system. So one way that's A is very costly and B leads to massive amounts of legacy code in the operating system, which just accumulates over the years. So one way to mitigate that problem is to sort of cut oneself a little more freedom in not supporting all the old applications and at one point just say this application will only run on the old operating system, but you can run it on the same physical machine, just in a separate partition. Finally, there's sort of consumer electronics-like applications like telephones or DVD players, another thing we heard. Of course, you can run all these things on top of operating systems, but if you do that, you don't quite get the same robustness characteristics as people typically expect from consumer electronics devices. So, I mean, people don't expect their telephones to not work because there's a virus infection or something like that. So one thing you can do is essentially build a standalone small telephone guest. Finally, there are a couple of sort of miscellaneous measures miscellaneous things one can do to improve operating system robustness. I've I've sort of summarized some of them as operating system monitors. So, I mean, today you have virus checkers. They typically run inside the operating system, which they're supposed to protect, where they are ultimately subject to attack by the things they're trying to protect from. Similarly, intrusion detection systems, all these things can in principle be moved out of the operating system and into a separate virtual machine where they're better protected. Another thought of the future, it makes it possible. There's been work on using hypervisors to actually move certain device drivers out of the operating system and thereby improving robustness. Good. So these were the kinds of scenarios we're trying to address. What kind of properties what does that imply for the hypervisor? What's important for us? So as always, isolation is one of the most important things we have to provide, and I'll say more about this on the next slide. Then performance is really important, at least for some of the applications, and in particular for server consolidation. I didn't give any quantitative measure here, but it is clear that we cannot afford to use designs which provide clearly suboptimal performance. Then assurance, very important, and also hard for me to quantify. That's why I didn't try to quantify it. So what I can say about it is our goal is to be significantly better than the assurance that exists in existing Microsoft products. At the same time, however, we got fairly clear management guidance against using methodologies, assurance methodologies or development processes that would either add significant cost or would be sort of fundamentally incompatible with the way Microsoft builds software. So I said I was going to give more details on isolation. So we're going to provide these partitions or virtual machines. They're supposed to be protected from each other, and the goals here are to protect confidentiality. If I'm doing computations in my virtual machine or in my partition, then no other partition should be able to observe what I'm doing, see my secrets, see my banking passwords, whatever. Same thing for integrity. You should not be able to tamper with my computations. So these are essentially the two goals we took over from NGSCB. A new goal is availability, namely that no collection of guests should be able to prevent other guests from executing unless authorized to do so. Unfortunately, we don't believe that we'll be able to meet this goal in the first release of the software, and I'll say some more about why we think that's going to be the case and exactly what the problem is later on. Good. So that's the end of the first part of the talk. That's the problem we're trying to solve. The next part I'll try to give an overview of the architecture that we're building. Good. First topic, extensibility. Of course, the hypervisor has to execute at the highest CPU privilege level, but it does that so the hypervisor is going to be a monolithic piece of code. There are no provisions for plugins, loadable kernel extensions, and in particular, there will be no device drivers in the hypervisor. So any kind of extensions will have to execute as guests in regular partitions. In order to enable this, we provide several IPC mechanisms, and I'll say later on what they are. And so this is sort of reminiscent of microkernels. This last remark here, new hardware constraints DMA devices. I think we talked about this last year. It's simply a reference to the fact that on today's PC hardware, you cannot put a if you put a DMA device under the control of untrusted code, you give that untrusted code unrestricted access to the entire machine, because DMA devices have unrestricted access to the full physical address space of the machine. That's going to change with the new hardware we expect. And examples of extensions or external components which would run in partitions, which would sort of support or extend what the hypervisor does with the device virtualization partitions, something that contains a disk driver and exposes something like a virtual disk to other partitions. Another example of an external component would be something that assists in administration or allows people to administrate or configure the access control policy of the hypervisor. Good. So I think the next slide just says the same thing in terms of a picture. So we have the PC hardware with one or more CPUs, memory, an interrupt controller, and a number of devices such as disks, network cards, graphics, all these things. Right on top of the hardware, we have the hypervisor. The hypervisor treats these different hardware resources differently. On the one hand, we have CPUs, memory, and the interrupt controller. The hypervisor knows how to handle them, and it's going to virtualize them, meaning that it's going to expose a virtual version of these things to each virtual machine. On the other hand, the hypervisor does not know how to handle devices. It doesn't contain drivers for these devices. So the only thing it's going to do with these devices will be access control, which means it's going to control which partitions will be able to access these devices, and these partitions will have to contain the device drivers. Good. So the hypervisor exposes any number of partitions and provides them with virtual CPUs, with a memory and a virtual interrupt controller. Inside these partitions, we have guest operating systems running, which may be anything from a regular operating system to a special purpose support component. If any of these, so as I said, device drivers live in guests. So if somebody wants to access the disk, there needs to be a disk driver in one of the guests. In the simplest case, this guest could simply use the disk for its own purposes, or if we want to go beyond that, it could essentially implement something like a virtual disk and expose that to all the other partitions. Okay. Next, partitions and virtual processors, the main abstractions that the hypervisor exposes to guest operating systems. So in these partitions, we have a physical address space, or something that looks like a physical address space. We have virtual processors, and we have a virtual interrupt controller. Regarding the address space, we're exposing a contiguous zero-based physical address space in each of the partitions. Of course, this is not the real physical address space of the machine, because there's only one address 0 in the physical machine. Then virtual processors. Each partition exposes one or more virtual processors, depending on how people want to configure their machines. Each virtual processor looks essentially like a real x86 CPU, and it gets scheduled on physical processors, and I'll say more about scheduling later on. We're also exposing a virtual interrupt controller. I'll say more about the virtual interrupt controller later on. We're sort of targeting different kinds of guests, or a whole range of guests. On the one extreme, unmodified off-the-shelf operating systems will have to be able to run with the help of external partitions. On the other hand, we're planning to do something which the Xen group called para-virtualization, which means we're essentially going to expose modified interfaces in the virtual machines which allow guests that are aware of the existence of a hypervisor to reduce the virtualization overhead. And this will require modifications in the guest operating systems. In the simplest case, the modifications can be encapsulated in device drivers, but in order to take advantage of certain interfaces that we offer, in general, kernel modifications will probably be necessary. So, control transfer. There are three ways of transferring control from a guest into the hypervisor. We're providing a mechanism for guests to make explicit calls into the hypervisor. Of course, that means the guest needs to be aware of the fact that the hypervisor is there. So there's a programmatic interface. It's being used for a number of purposes, but sort of the main purposes we can think of here are sort of interfaces on how to configure the hypervisor. For example, saying how many partitions should be running, how many virtual processors each partition should have, configuring the access control settings. And then, of course, there are these some of these modified interfaces are there for performance optimizations. Second way to move control into the hypervisor are just traps. If a guest executes a privileged instructions, the hardware will trap into the hypervisor, and well, that's just the second way of getting into the hypervisor. And then, of course, there are interrupts, including hardware interrupts. So the way we run the hypervisor receives all interrupts and inspects them and may essentially route them to one of the guests. And as I said, there'll be more on the virtual interrupt controller later on. So next, device management. The goal here, so there are several goals, and these are sort of long-term goals. First of all, we want to enable the vision is that we want to enable arbitrary assignment of devices to partitions, meaning I should be able to assign the disk to one partition, assign the network card to another partition, or assign both of them to the same partition. In any case, there should be no a priori restriction on which partition should be able to access which device, or whether that all partitions should only be able to accessible from the same partition. All devices should only be accessible from the same partition. So we're really envisioning a fairly general assignment of devices to partitions here. At the same time, when we do that, there needs to be protection from DMA devices. So if I put a DMA device under the control of an arbitrary guest, then this guest should not be able to interfere with other DMA devices, and it shouldn't be able to interfere with anything else on the machine. Another goal is to keep the real physical addresses opaque to guests, which essentially allows us to do a whole bunch of things underneath the guests.
Do you expect guests to be able to share devices?
It will be possible to. It should be possible to configure the machine such that will be possible. Good. So on existing, so this is the vision or the goal, and the problem with existing hardware is that it does not work on existing hardware. So first of all, on the hardware that existed up until now, there were absolutely no DMA hardware protections. The hardware protections that we expect to get in the first round of the initial version of DMA hardware protections that we expect to get will be insufficient. I think we described these hardware protections last year, and it's essentially they're lacking expressive power to say this partition should be able to access this device versus another partition should be able to access another device. Another problem is that today DMA devices operate on physical addresses. So if I want a guest to operate if I want a guest to take control of a DMA device, it needs to know what the physical addresses are, which conflicts with our goal of keeping the real physical addresses opaque to guests. So in order to change this, in order to solve these problems, we think we require hardware modifications, and we're working with our hardware partners on this. Two things here are a second level address translation, which means in addition to the existing virtual to physical MMU hardware that exists on the PC, there would be a second level of address translation, which sort of maps the guest physical addresses to the real physical addresses. One thing that would allow us to do would be to essentially run DMA devices of something more or less akin to virtual addresses. And another benefit would be we could essentially use the standard techniques that are currently used to constrain the CPU, to constrain the DMA devices transparently. Yeah. That would be helpful, but again, this is stuff that's being worked.
If everything goes well, when my computer supposed to have that?
I can only guess 5 years, but it's a wild guess. Good. So now comes a slide. So far I've described what we're planning, what our long-term vision is, and also what we're planning to do for the first release of the product. This slide summarizes the limitations of the first version of the product, which sort of falls all the ways in which it falls short of our long-term goals, and these things are actually quite significant. So they all sort of revolve around the fact that the hypervisor will have to rely very heavily on a special partition, which we call the primary partition, which is probably going to run Longhorn. So number one, we're not going to, in the first version of the hypervisor, we're not going to build our own scheduler. Instead, all the partitions will be scheduled by the scheduler in this primary partition. Of course, the moment we do that, availability pretty much disappears. Second, similar thing for memory management. We will, essentially the hypervisor will have to acquire any memory that it uses and that it gives to its other partitions from the primary partition. Right. So the first two limitations are essentially the result of our product schedule. So there's no real hard technical reason behind it beyond the fact that it looked like it would take us too long to do these things in the first version. I'm not sure if that's a satisfactory answer, but no, it can't destroy the integrity of the memory, but it can prevent the hypervisor from getting more memory. So once the hypervisor has actually gotten memory from the primary partition, that memory is protected from access by the primary partition. But if the hypervisor requests memory and the primary partition refuses to give it to it, then the hypervisor will not have that memory. Yes.
And it gives it up to the primary part.
Yes. Yeah. Yes. Yes. And sort of. So let me say some more on this product schedule thing here. So there's sort of a couple of some of the more difficult or things that sort of looked like they might cause severe schedule problems revolved around the interaction with Windows and sort of getting this primary Windows partition to work the way Windows is supposed to work in the presence of a hypervisor. So one example, so one of the scheduling problems we had was that Longhorn is going to have a real-time scheduler with actually fairly tight real-time requirements, which come from the multimedia people. It looked like a daunting task to sort of build a virtualize that real-time scheduler. The memory management was a similar problem. We getting things to work well with Windows seemed to require a certain number of modifications in the Windows memory manager, and we just didn't think these changes were going to happen. So finally, device management. The hypervisor assigns. The reason for the device management limitation is hardware, mostly hardware availability. So the hypervisor will assign almost all the devices to the primary partition. That's mostly the result of the sort of limited expressive power of the existing DMA protections. Another thing is we'll have to run the primary partition in V equals R mode, which means the primary partition, the physical addresses that the primary partition sees are the real physical addresses of the machine.
It might help us to understand this. If you could explain, how is this different from the old Palladium one?
It is actually...
Because the difference don't seem to be very great. It's easy to understand why it's very close to the original Palladium plan. So rather than going through all the details of your new plan, it might be helpful to just tell us how it differs from the old one.
Yes. Okay. Let me see if I can summarize that. So everything that's on these slides on this slide here is essentially identical to the old Palladium plan. How does it differ? There's going to be better support for virtualization in the non-primary partitions. So you will be able to. So for example, the non-primary partitions are going to see a zero-based non-contiguous zero-based contiguous address space. Another goal here is to sort of keep these limitations as as transparent as possible to the guests, meaning that yes, there'll sort of be a reduced, if you want, security or availability, but it should be, the goal here is to be able to build a second version and have sort of plug this in underneath existing guests and have them run on the same interface, providing now full availability without really changing the way guests interact with the hypervisor.
In version 1, the guests get a virtual CPU and memory. In version 2, they get devices. What you just said? Or in version 2, they get availability.
Yes, in version 2 they get availability. Device management is so we're.
Devices are up for grabs.
Devices are up for grabs in the so for most guests in version 2 I would still expect them to sort of receive device support from some virtualization component, but there'll be a broader range of configurations that allows different kinds of virtualization components to exist. Right now there's going to be only one virtualization component which is essentially in the primary partition. Mm-hmm.
Are there things that could be done there that would make it work better out of the box on this sort of thing?
You mean optimize performance of Longhorn on top of a hypervisor?
Yeah. On top of this hypervisor and not necessarily optimize performance, just optimize to get rid of some of the bumps. I mean, in the days when you were running Windows 2000X on Palladium, it was arguable that, okay, we can't change the Windows software because it's already out there and so on. It seems like who knows when this will come out relative to Longhorn, but whichever way it happens, it seems like Longhorn isn't being built in a vacuum. It's being built by the same company that's looking at this. Whereas you don't want to have one depend on the other. It may be that there are structuring decisions that can be made at Longhorn to avoid some of the problems.
Yes. So on the one hand, we are working with the Longhorn people and we're driving a number of modifications into Longhorn. So the nature of these modifications is sort of mostly. So it's mostly things that are relatively easy for Longhorn to do, and they're mostly a couple of performance optimizations. We've talked to them about changing the scheduler and doing things to the memory manager, and it just there's a trade-off between delaying Longhorn and accommodating the hypervisor, and I think the trade-off that was made was to not delay Longhorn too much. So I'm not sure if I answered your question, but we are working with Longhorn. We're asking for a number of things. We're getting some of the things, but not all the things, and these things that we didn't get.
Well, does that mean that if you succeed, then this will lead to a larger rewrite of Longhorn, or whatever the successor is, so that things can accommodate the hypervisor, or
if we succeed, then I would expect further changes in Longhorn.
Like the hard changes, because you said they were hard changes.
Yes.
That would be even harder then.
You mean harder because Longhorn will have already shipped?
Yeah.
Yes.
The successor needs to ship with a rewritten memory manager, even though everything that uses it is there on top, and you've got all this compatibility on.
Yes. And I agree. And yes.
You have to understand what's going on with that. Longhorn is basically MT. It's not that different. The areas that we're now discussing from MT that we have today. That's point one. Point two, the plans for hypervisors, Palladium, and all that stuff have been changing about every 6 months. So they don't have a lot of credibility with the Longhorn. So it's very unlikely to get the Longhorn guys to do anything that's not extremely easy for them to do, because they're just not going to believe the whole plan. And it's going to take several years to sort that out.
The other thing is that somebody who needs to print press knows that different press with further advanced.
Really very complex question is whether there's anything you can do in configuring or locking down Longhorn or whatever that would make Longhorn a more trustworthy partition one.
Yes. I think the answer is yes, and I think the next talk will be all about that question.
In particular, the devices, long-term model that potential devices can be run in separate partitions.
Mm-hmm.
It will be, that is, I don't trust my video card, so for the driver port, so I might want to run it in a different partition. Windows from Crank.
Yes. I'm not sure.
That's the first version of the hypervisor.
Do we?
No,
Sorry, I didn't hear the.
what the larger vision is for the role of devices within Windows relative.
What you're asking is, are you going to get the device drivers out of the kernel or isolate them somehow?
Even, I'm saying maybe newer drivers or whatever could be moved out, or maybe totally could be isolated by moving them in separate partitions. Is that an explicit goal?
So that is currently a well. It's with respect to Longhorn, it's simply an idea we've been tossing around. I don't think it's anything like an official goal or a plan. There's been work outside Microsoft and inside Microsoft on sort of future operating systems, which sort of envision being able to take device drivers out of operating systems. But for Longhorn, it's really more of an idea than a plan. Okay, one slide on assurance measures, and there's only one slide on assurance measures because we're going to have an entire talk on assurance later on. So this slide here sort of summarizes what we believe are the most important assurance measures we have to think of in the design, and this sort of reflects our conversations with Steve Lipner. So number one, precise specifications, and in particular precise specifications for the externally visible interfaces or externally visible behavior of the hypervisor. So at the boundary, at the external boundary of the hypervisor, and we're also going to do that for the individual subcomponents of the hypervisor. Current plan is to essentially rely on informal methods, informal specifications. Second important aspect is a layered design, and we're still trying to figure out on how to do still working on how to do the layering. Third, and very important, and probably most important for this talk here, keep the system small, and it's also very important relevant for this talk because a lot of the design decisions that we're making are the direct result of our desire to keep the system small. And then there's going to be a whole array of other measures which are going to be discussed in the Hayes talk later on. Good.
Are you going to talk about the extent to which the system is small or
Why don't you ask the question now?
So it struck me there were various places where you provide multiple mechanisms that do more or less the same thing.
Okay.
Like communications. So if one were being draconian on keeping the system small, you would say you should never have multiple ways to do something that's similar. You should only have one way. So how are you making decisions about those trade-offs?
How are we making decisions? I think in principle, I agree with you that the way the decisions come about are sort of so there's one class of duplication where we're saying, well, we provide the legacy interfaces, and we also provide these optimized interfaces for performance optimization. So that there's a trade-off between. So in this particular class of duplication, there's a trade-off between performance and minimizing the TCB, and that's sort of, we're just making this on a case-to-case basis. And if you or the board have any feedback on whether these trade-offs are the right trade-offs, then we.
So you're making performance TCB things as opposed to performance assurance things. Seems like it's always performance versus assurance. And if that's the case, then you need to ask the extent to which this performance, how much more complicated are you making things to get how much performance?
Yes. So, and I think we're asking this question on every single performance optimization we stick in there, and we hope. So the criterion should be that for a little bit of additional, for relatively small additional system complexity, we get a good deal of additional performance. So we'll, of course, one should really look at this case by case and revisit whether we really made the right trade-offs here.
Me and Ron on this, but it's hard to get excited about this given that you're requesting Longhorn anyway. In the long run.
Well, what are you testing on before?
Well,
The same story we had with Palladium, right?
what did that come back to?
Yeah, but we know from the Palladium story that in that security, device multiplexing is screwed up. You just lose availability.
Yeah.
Availability, right?
Yes. Right. So
This is the same story as the Palladium story, guys. Remember, it's not new and different.
That's going to be what Palladium was from the line B, because I don't think we're ever going to get to this long-term vision.
No, I'm not.
yeah.
Are you doing any COVID channel analysis?
Currently not, and it's something we need to think about. And if you have any feedback on that, that would be good.
I mean, it seems big when you're sharing.
Excuse me?
You're sharing devices.
So, yes. So devices are sort of one thing that the hypervisor doesn't really control. So there would have to be the covert channel analysis on in these external components that deal with devices. For memory, yes, we'll have to make sure that we don't leak information, and there's currently no plan for real covert channel analysis.
So you gave two reasons why you don't want to go to a full-blown virtual machine without dependence on Longhorn. One was schedules, the other one was hardware for various devices.
Yes.
How serious are these reasons? It seems to me that both of them are fairly weak. Can you comment on that?
So the schedule thing was essentially the memory management and the scheduler. It's as we said before, it's largely a question of our interaction with Longhorn and making sure that Longhorn can run on top of the hypervisor in a essentially high-performant way. So in order to do that, we would require certain changes to Longhorn, and it just looks like these changes are not going to happen.
So you'd say any virtual machine that's running Longhorn is going to have this problem?
Any virtual machine that's just running Longhorn. Well, no. I think what I'm saying is we could have opted. So we could have opted to build a hypervisor that, for example, breaks the Longhorn real-time scheduler. So then we would. So we could have just built a very simple scheduler into the hypervisor. The result would have been that none of the guests would have had the real-time guarantees, which would have meant that the multimedia people who were trying to run their DVD players and music players on top of Longhorn would have been unhappy, or some of their functionality would break. So I think that was sort of one of the main problems around the scheduling decision. So it would have been. So we probably could have built a fairly simple scheduler into the hypervisor. It would have sort of meant that when Longhorn runs on it, it doesn't have the full functionality, or performance is bad. And the trade-off was made to have Longhorn work at full functionality.
Let me ask the question this way. I really like the vision, but suppose I take off my sunglasses and accept the premise that Longhorn is here to stay in this weird configuration where it actually has a lot of control over things that a purist would put in the hypervisor. Why bother with the hypervisor?
Why not just get Longhorn?
What's the long term in the world where Longhorn really does figure prominently in the picture, and you can't move to a hypervisor that's more pure?
You're saying to virtual PC on top of Longhorn rather than a hypervisor underneath or something like that?
That's one implementation, but I don't want to commit to being so kludgy. Maybe I'm wondering, given that Longhorn's going to control a whole bunch of pieces of this functionalities of this hypervisor, what exactly are we getting with the hypervisor that, in that world? Maybe we don't need it at all. Put the applications into Longhorn directly. So, I mean, I understand I just pulled the rug out and asked you to defend it.
Are you saying go back to the Palladium design?
Everybody, am I saying a solution? And I'm not saying a solution. I'm asking to have articulated just a class of benefits.
Well, we know what the benefits are from the Palladium design, right? You don't get availability, but you get isolation. The difference between this and the Palladium design is that in the Palladium design you had a totally different VM that you had to program to if you weren't the main guy. And here you get a VM that's the same with respect to the essential resources of processor, memory, and interrupts.
Yes.
That's the difference. take it from there. Now answer your question again.
Well, that's the benefit, right?
Yes.
Yeah, I mean,
But so I guess
Does
it's
that
not.
answer your question?
it spalls it, so I don't.
So I'm sure I'll well, I sure better write this, but it's not obvious to me as much as multimedia is fun that the fact that you might break multimedia. I mean, it's not given that you're going to break multimedia. It doesn't, with all the damn resources on the computer, probably run great. No one will be able to notice, but you might break some of the guarantees there. It's just not obvious to me that that's the right trade-off.
Okay.
You might compromise some of the guarantees when you're running multimedia. I would think a whole lot of people, especially if you're running servers and stuff like this, would think, don't give a damn about that guarantee, and really give a damn about isolating device drivers and stuff like that. And in fact, if the whole industry's in jeopardy because of this, what's happening with security and viruses and all these things, games theoretically games running a little slower and not having a hypervisor, it isn't such an obvious trade-off to me. So maybe let me ask. So
Multimedia is over-provisioned anyway, so you're not going to squeeze the last cycle in any case. So the fact that multimedia performance is not going to be great is not a good reason.
It's
not
not
a
even-
believable
Wait,
reason.
so you guys are thinking just of PC. Longhorn is intended for a lot of other.
what?
Longhorn is intended for a lot of other devices.
You mean it's for embedded devices?
Well, certainly, entertainment devices.
But these systems are over-provisioned for those anyway. You're not operating at the last 10% performance. I mean, so I don't find this believable.
You'd agree that servers won't. It's hard to understand the server application, the importance of servers for this. So there's a pretty large class of computers for which this compromise isn't obvious, and it's not so. I'm kind of skeptical in practice how that people won't be playing video games on top of other people's virtual machines. I guarantee. That's going to happen, right? And other devices. I mean, and embedded devices are going to run other people's virtual machines. It's kind of funny that it'd be interesting if that's what you need to do to run. If you want to run a real virtual machine running Longhorn, you have to get it from somebody other than Microsoft.
So, okay, yes. So that's good feedback, and I certainly see the points regarding the scheduler. But the thing here is that the scheduler and the memory decision were essentially our decisions. The device management decision is essentially a hardware availability question, and there's not much we can do about that.
Well, what does VMware do about that?
ESX server or.
What do you mean?
So what does VMware do? Like in the hosted version of the virtual machine monitors, the host operating system takes. It's very similar. The host operating system takes control of all the devices, and then virtualizes them and hands them out to the individual partitions. But you have essentially some host operating system, be it Windows or be it Linux, take control of all the devices. Okay, should I move on? Good. So the rest of the talk goes into some of the more detailed design decisions we've been making, and the goal here is mostly to solicit feedback on some of these decisions. Good. CPU. So we're going to expose a virtual processor abstraction. Each of these virtual processors behaves essentially like an x86 CPU. That means the hypervisor will have to emulate certain privileged instructions and CPU state like control registers. So if you look at the instruction set of the x86, it's fairly large, and there's a fairly large, there's a reasonable number of different x86 models from AMD and Intel. So there's a summary is that there's a number of there's quite a large number of instructions. Some of them are very complex to emulate. So one of the things that we're planning to do is to enable external handlers to emulate certain kinds of instructions which are sort of not very frequent or very complex to emulate. The goal here is to allow us to not change the hypervisor every time some new instruction comes out somewhere. Another thing we do is, so the interface is to read and write the state of these virtual processors, and so beyond the actual x86 CPU state, the virtual processors can be in sorts of different states. So they can be ready, which means they're ready to be scheduled. They can be running, which means they're currently scheduled and running on top of a physical processor. They can be halted, typically as the result of executing a halt instruction, or they can be blocked, for example, because they executed a privileged instruction which caused a trap into the hypervisor.
By having this extra readable register, you enable somebody to write a scheduler on top of it. I assume that list of BP states were part of external read-only interface by the processor. Is it? Can a virtual processor find out the BP state of another virtual processor?
Of course, there's some access controls around it, but yes.
And that's so that you can build the scheduler in a partition.
Well, the goals, actually, the primary goals were facilitate debugging. Another thing was for things like if we want to run unmodified legacy operating systems, we'll need something. The plan is to enable that by. So these unmodified legacy operating systems are going to cause all kinds of traps because they just execute privileged instructions all over the place. The plan here is to enable them by means of some sort of a monitor partition, and the virtual processors in the monitor partition control what the legacy operating system does, and one of the things they have to do is be able to look at the state of their virtual processors.
So you don't imagine that the monitors are going to change the state of the processor from block to running?
So this interface here is so this interface up there is not referring to these states down here, but it's referring to like what's in the CR4.
You see why it might be confused. It said right BP state.
Okay. Yes, I'm sorry about this.
Those BP states are really hidden.
Yes. Memory. So as I said, each partition exposes a zero-based contiguous physical address space. Once again, there's been a performance complexity trade-off here. On the one hand, we're exposing x86 compatible MMU abstraction, which essentially supports all the addressing modes of existing x86 processors. We're exposing a second MMU abstraction, which is supposed to allow us to virtualize it at lower overhead. What's next? We're hiding physical addresses from the guests, except for the primary guest, which is running in V=R mode. Which means we're going to have two levels of address translation in the absence of sort of fundamentally different new hardware. The thing I described earlier. These two levels are essentially going to be implemented by means of the shadow page table algorithm. So Next, interrupts. So the hypervisor takes all interrupts, which means it will have to take control of the APIC, which is the hardware interrupt controller on the PC. At the same time, it exposes a virtual interrupt controller to each partition. This virtual interrupt controller, which we call synthetic interrupt controller, has all three functions. It exposes the legacy APIC hardware interface. It once again exposes a modified interface for reduced virtualization overhead, and it exposes the third thing it exposes is something akin to Unix signals. So what this APIC typically allows you to do is to send an interrupt to a different processor, and on the physical machine there is just one partition, so you just send it to a different processor on your same physical machine. That has been extended slightly to allow any virtual processor to send an interrupt to any other virtual processor, even if it's in a separate partition, and that's sort of the first basic IPC mechanism which gives you something like Unix signals. Yes, beyond that, you can attach small, constant-sized messages to this.
Why is that? There's this hypervisor instruction for sending this.
Yes.
They sound like they're pretty similar.
Yes, they are similar.
Want to say a little bit about why they're what it is?
Well, the primary overhead in these architectures is IPC. So, having hardware support. Could have the potential of drastically cutting a lot of the overhead.
There are two mechanisms. You pick which one you think is the cheapest, and we'll get rid of the other one. But, well, actually, there's three. There can be three, at least three. But as I just want, I don't have a strong opinion. I just want to, when I hear,
I think when you try to pick one, shoehorn it in, and what you end up with are optimization tabs. That's that along that one mechanism. That essentially get you back to this.
Okay, so actually I see Fred's point, and I don't think we have a very strong, at least I'm personally not a very strong believer in these two different messaging mechanisms. But and if you think one of them should go, then that would be interesting feedback. The messaging mechanism. So these messages here are essentially, the plan is to build them straight on top of this synthetic interrupt controller, on these synthetic interrupt controller messages. So they're almost just like a different kind of a very small wrapper layer on top of this synthetic interrupt controller signal. So it's probably not going to add a lot of complexity. It's not clear to me how much value this particular type of messaging adds.
I assume you can have arbitrary sizes.
So so that would have made more sense, I think. So, the general approach that we took was to say we're not going to build anything complicated into the hypervisor in terms of IPC. We're going to expose shared memory and allow guests to essentially build their favorite IPC primitives on top of that. That's pretty much what the Zen group did, and anyway, so that at least that was our approach. So the
But for that approach, you would want to build synchronization mechanisms in the hypervisor so that I could use the shared memory for communication and I could use the hypervisor mechanism to synchronize the piece of that.
yes. So we're building right. I mean, the one thing that's not on this. I mean, in terms of synchronization, the one thing that's not on the slide, but which is available to guests is essentially the sort of test and set style CPU instructions, which allow guests to sort of build their own synchronization things.
But that's spinning. Yeah. And I don't think you want to spin on a hypervisor.
Okay, so. Okay, no, but this is actually very good. So I mean, maybe we shouldn't spend a lot of time on this, but this was one of the areas where I think I'd really appreciate feedback on what are the right IPC primitives to expose.
So let me just structure that better. That's an open question, and it's not easy. It's a too ill-defined question for me or probably to write you a good message. That hearing all these kinds of details and having somebody like to push back on the design constraints and having a dialogue is a much more sensible way to get the feedback.
Okay.
I don't know if this is the right time to do it because I don't know what you wanted to cover, but at least I have an understanding that this is an area that needs further revisiting, I guess.
Okay. Good. So we'll
do something.
Right, we'll have to figure out how to communicate on that. Good. Let's move on to the next. I mean, just to say it again, each of these detailed areas I've picked because I had doubts about whether we're doing the right thing, or I wanted to ensure that you agree that we're doing the right thing. So any of these things here are sort of ideas at a fairly early stage, and any feedback you can give us on them will be very valuable. Access control, next topic. So Hypervisor will implement a simple access control system, but it will leave certain things, but sort of certain complex things will be left for external partitions to implement. Let me say what I mean by that. So the only subjects that the hypervisor knows are partitions identified by, let's say, a partition number. It doesn't know user identities. It doesn't know user identities. Doesn't know code identities. The objects are essentially the simple hardware and hypervisor resources that exist on the machine. Things like pages of memory, certain CPU registers called MSRs, memory map control registers, I/O ports. So these are the kinds of objects to which we're trying to control access, and we're essentially trying to provide some basic support at least conceptually, along the lines of for discretionary access control, along the lines of an access control matrix, which simply says which partition has which right to which object. In addition, we're trying to provide basic support for mandatory access control in the form of let's can envision it as a matrix which says which partition is allowed to send information to which other partition. I mean Mac.
Mac just says that the subject can't, that the owner of an object can't decide who can access the object. My understanding of the
Okay.
Mac and Mac is who says who can change the access control name. And the thing about who can send information to who is when you start tagging things with secret and so on. That is a mandatory access control regime, but it's a particular one called MLS. What do you mean when you wrote MLS?
Okay, so what I meant was it should be what you said about objects should be possible. It should be possible to configure the system in a way that the owner of the object does not get to, or that whoever created the object, well, most of these objects don't get created, but that whoever, there's a distinction between who can access the object and who can change the access rights to the object. The additional thing that, so there's one additional thing in here which is think of it as a matrix that says, matrix which has the subjects on the rows and the columns, and it essentially says which subjects can send information to which other subjects. There's no labeling inherent here, simply a matrix that says partition 5 may or may not send information to partition 7. It's possible so the goal is to make it possible to build to build labeling and MLS and other mandatory access control policies on top of that, but we're not planning to build labeling into the hypervisor.
Okay, so I understand what you mean. How do you define send information?
Essentially, I look at the different IPC mechanisms we have, and so look at the different IPC mechanisms. So one thing is messages and these interrupt things. So that's pretty obvious. As far as the only remaining thing is shared memory, and in shared memory, it's sort of send information means I have there's a segment of shared memory, and I have a write. So one partition has write access, and another one has at least read access.
So you're going to check that this graph you're not allowed to send has all is a transmitted.
Yes. And again, if you have any feedback on how much sense that makes, that would be good. Anyway, but one fundamental design decision here is to leave certain things out of the hypervisor. So we're not associating any meaningful security principles with these partition subjects. So things like user identities or code identities will have to be implemented outside the hypervisor. Main reason for that is that there's just a whole variety of sort of user authentication methods and different notions of code identities, and there doesn't seem to be general agreement on what to do. There's a wide variety of different things that people do, and they all look fairly complex. Similarly, we're not implementing concrete MAC policy types, and if somebody thinks that they need them, but the goal is to make it possible for somebody who thinks they need them to implement them in a partition. So essentially, an authorized partition will be able to call into certain hypervisor interfaces and set these essentially set these access control rights. So it does not have to be the primary partition who sets that. Yes, so there's a bit of a bootstrapping problem here. Yes, and that will. I think so we have some ideas on how to deal with that, namely by essentially which is sort of gets merged into the hypervisor boot process. Essentially when you boot the hypervisor, you already you have some out of a separate mechanism to tell the hypervisor about which partition is.
So you have a root partition.
Yes.
I think you're portraying this in the wrong way. Let me try to portray it in a different way that would have made it more compelling. If one of the functions of this hypervisor is to provide isolated partitions, the security vision as opposed to the PC vision, and you have a hypervisor in which partitions can communicate, then the only way to have isolation is if you can say, well, this petition really isn't going to get bothered by this other thing that's untrustworthy. So it's not that you're implementing a security policy per se, is that you're ensuring the isolation that you want in order to trust the partition. And that's why it makes sense to have this kind of a mechanism. Not necessarily because you're going to implement some fancy security policy involving lots of partitions, which you might end up doing with this mechanism, but because you really need it for the isolation, or else an untrusted partition can harass a trusted partition by sending it messages, and maybe it'll just corrupt it out of service, maybe it'll aggravate something else. Check that or
it's so yes. I don't reject it. I'm not sure that one would need mandatory access control to sort of to allow protect.
You need a matrix that says you can send stuff to root, and that's what you said your MAC was.
Let me rephrase that somehow. Suppose that you have this virtual machine architecture in which the partitions are totally isolated. And then in some controlled way, you want to relax that isolation so that it's a partition communication. But that relaxation, that controlled way has to be described in some form.
Right.
Whether you call it mandatory access control or not, it's irrelevant. But we have to have a specific way of relaxing that information.
Yes.
That has to be very precisely defined.
And you think that's what you meant by that MAC word? Now, if that
Yes. No. I think that's a good way of putting it.
So your over communications through IPC, Hypervisor or the other.
Yes.
We'll revisit that.
So, well, the very strong feedback we get every time I mention the words MAC or covert channel is that we should not bother with it from a variety of people. So
that's not what we were telling you.
And we can talk a little more about that in the presentation.
okay, well, I mean, so if well, then that's very good. Please write that into your feedback. But at this point, I didn't feel like I could make a strong enough case to convince people to actually do it.
I mean, a case that convince you, and now that we know what the over channels are, we were to show you the channels less reasonable sharing devices, for instance.
Right. Right.
I want to talk more to you about it.
Okay.
Sure. Because I actually agree with what Martin said. We kind of put plans in place right now that don't include much over channel analysis, but we are very interested in working with you guys. I know yourself because.
Well, no, the interesting piece of information that I wasn't aware of is that someone else is saying no.
No, I was going to say, I think the primary person who's saying don't do that is they stepped out of the room.
Yes.
I intentionally asked the first covert channel question when he was in the room. Unfortunately, I think he might have been having a side conversation with Brett. I asked that because I thought that might be
Overtly asked. The issue is whether the customer base is interested in covert.
Well, I mean, I think it's whether or not they're interested in isolation. Really interested in
How strong is
how
isolation?
strong they're interested in isolation. Talking about a server farm on the center of the platform or something like that.
Okay. So this. So the next. So I think there are like 3 or 4 more slides left in this talk, and they're all about one particular area which I which I went into particular detail because I wanted to get some feedback on it. So, and it revolves around control transfer and the design decision to make the hypervisor non-preemptible. So once again, remember the previous control transfer slide, which said that there are these three different ways of getting control from a guest into the hypervisor, namely explicit calls into the hypervisor, traps, and interrupts. Now, once control has been transferred into the hypervisor, pretty much we've made the design decision to make the hypervisor non-preemptible, which means we are turning off interrupts while the hypervisor is running. So one of the things that means is that all code paths must be short and predictable to avoid excessive interrupt latencies. Also, there will be no worker threads or worker virtual processors, which would be sort of waiting on synchronization objects inside the hypervisor for something to do. So the goal here, or the idea, is that making the hypervisor non-preemptible is going to simplify it significantly and reduce the state space we'll have to deal with. Of course, we'll still have to deal with concurrency because we'll be running on multiprocessors. Anyway, but we believe the benefit that that's going to give us is going to be a simpler hypervisor. And of course, the difficulty is that we're imposing constraints on other aspects of the design, on the internal design, and also on the interfaces. As I said, all entry points must lead to short and predictable control paths. So another more difficulties arise if we take some other circumstances or design decisions into account. Namely, not all calls that we make into the hypervisor can actually be handled entirely by the hypervisor. Some of them may actually end up calling into, well, at least in the first version, into a primary partition or into one of these external trap handlers. From the point of view of the hypervisor, what that means is that any call out into the primary partition may potentially never return, and even if it returns as expected, it may take a very long time, which is a problem for the short and for the requirement of having short and predictable code paths. So I've sort of tried to illustrate this here on this slide. On the left-hand side is sort of the ideal or easy case. You have, let's say, an explicit call into the hypervisor to modify modify the access control settings in some simple way. You call into a hypervisor, it flips some bits somewhere and comes back. So that's what I would consider short and predictable. On the other side that's sort of the problematic case. Let's say there's an explicit call into the hypervisor to create a new partition. That new partition is probably going to require some amount of memory to be set up. And, well, given this initial design, that memory, the hypervisor may have to call into the primary partition to actually obtain that memory, and the primary partition may take arbitrary amounts of time to come back. So how do we deal with this problem? The problem being that some control paths are obviously not going to be short and predictable. So back to the previous slide here.
I understand what's happening. I'm not debating that it's true. But what I'm wondering about is why is it a problem that there are unpredictable?
So if we make the hypervisor non-preemptible, and which essentially means turning interrupts off, we create if we execute in the hypervisor for a very large amount of time, then the interrupt latencies will become very long.
I agree, but I didn't see that on that memory picture. Do I see I see that as there's two hypervisor calls.
Yes, and that's pretty much what yes, precisely. So that's what the way.
It's a clear interface, but you guarantee the hypervisor executes in short chunks and
Yes.
you understand, and you get all the benefits.
Yes, and right. So that's essentially where we're going. So only the hypervisor itself is non-preemptible, but the service partitions are preemptible. So the moment you leave the hypervisor and call into the primary partition, you turn interrupts on again. So one last point is what does that mean for the virtual processor that initiated that call? It's still going to be blocked until the call completes, but it may take interrupts. But on the other hand, we decide to let it take interrupts while the hypervisor is not executing. Well, so they all get queued to the hypervisor. The hypervisor then looks at the interrupt and passes them on to, and in many cases, well, depending on what the interrupt is, passes them on to one of the virtual processors.
But that, I guess, may is the operative word. If you don't want it to take interrupts, then at the time you make the call, you can ask them off. So you're creating the most flexibility at no cost.
Okay, but so the problem is that so we have devices will be under the control of virtual machines. Devices, so some devices have rather strict constraints on interrupt latency. So if there's this let's say the virtual processor which is being blocked is the virtual processor that's the virtual processor running in the disk virtualizer. If we just keep this thing blocked for arbitrary amounts of time, then my disk might stop working or my modem connection might get dropped.
So I understand it. I think the question that's been in my mind since you started this three-slide thing is you need to articulate what is the hypervisor guarantee?
Okay.
What can I assume, as a customer of the hypervisor, what can I assume? If I can assume that I'll only lose control for this amount of time, or there's a whole list of things, and there seems to be one associated with losing the processor and it leaves uncertain delay and so on. Once you articulate that, then if you deliver on that spec, then people will build around it. So in the case of this primary machine, partition that's running the I/O, it will know not to make hypervisor calls when an indefinite delay can cause it to lose interrupts that it. Okay, that makes sense.
So, let's come back to the original goals.
Real quick, we got like 5 minutes here, and then we go into the break. So, we're wrapping up.
This is the end of your talk.
This is there's one more slide.
We got a half-hour break after that, so if you want to have sidebars about it.
No. We want to bring this up here. Why don't you do the last slide?
Okay. So last slide is essentially a slide with questions and areas where feedback where I'm hoping to get some kind of feedback in, and then we have to talk about how exactly we structure communication, but areas where I'm sort of actively seeking feedback is also of all these points on which I went into detail. What do you think about them? And so, for example, the IPC area. Another thing I've been trying to work with Steve Lipner on a layered design. We've run into some roadblocks around the which seem to be related to the fact that we're making the hypervisor non-preemptible. So any thoughts on how to do layering here would be interesting. One area which I haven't talked about at all, because there wasn't much to talk about based on how far we are in the design process, is resource management. It's major area of difficulty. Any suggestions or pointers you might have? would be very valuable. And yeah, what are the right assurance measures, and that we should probably discuss after the last talk.
Okay, so let's come back to the original goals that you had for version 1, confidentiality, integrity, but not availability.
Okay.
Looking at the design, the question is it possible that you could miss in some of the partition, not the primary one, you could miss some interrupts because the primary partition misbehaves?
Misbehaves in...
Well, so suppose that you have some sort of a flooding attack on the primary partition.
What?
Flooding attack.
Okay.
There are some bad resource quotas, and somehow the primary partition keeps spinning and doing not much useful work. And as a result of that, you might lose some interrupts in some of the other partitions.
Mm-hmm.
If that happens, I don't see how you would possibly provide strong integrity guarantees in the other partitions or strong confidentiality guarantees in the other partitions. So I'm not talking about availability now.
Mm-hmm.
So you really have a strong or weak, I don't know yet, but you have a dependency on the primary partition for the operation of the other partitions in some way. So I'm wondering how bad is that dependency? In other words, what guarantees can you provide for the other partitions?
So I think part of the question is sort of, part of your question is related to resource management. How can we sort of...
It's not just resource management. If you start missing interrupts in the middle of a transfer,
yeah.
in the middle of a file, the file will get corrupted.
Yes.
So where is integrity?
That's true. I mean, it's sort of unlikely to come up initially because we're sort of putting all the devices under the control of the primary partition to begin with. So it may. I see that. I see the problem you're raising. It may not arise in practice in the initial versions. But yeah, I agree.
So the devices in the version 1, all devices are under the control of the primary partition?
All of them except for certain NGSCB devices, and I think the next talk will I'm not quite sure in which way they use interrupts. So I think the next talk will go into that.
My question then is moot because the integrity and confidentiality and availability all depend on the primary partition.
Isn't that true?
Isn't that true?
Because the primary partition can do something terrible and you screw all the others.
No.
Gets the device stuff encrypted and on disk and so on, so that one prosecution can never see it. One prosecution doesn't have access to the memory. It's been allocated to
Disk
disk.
access is why not complete.
So yes.
So you can't lose confidentiality now.
Right.
Certainly the primary can compromise availability.
Well, that we know, but what about integrity?
So so are you concerned about file reading and writing files? I mean, so the plan here was essentially to use the, I mean that still, I mean you can essentially use the old NGSCB plans which are essentially use the crypto chip on the motherboard to encrypt all your communications with the disk and use some of these hardware counters to make sure that you got the last version.
No, but your encryption may not work.
Why not?
Well, if you start getting these errors, is it all hardware encryption? Yeah.
Well, no, wait. So let's say I want to write a file to disk. I have some data in my memory. I want to write them to disk. I run my partition. I have my partition encrypt the data in memory, and then put whatever. I mean, by encrypt I mean encrypt and integrity protect them. And once I'm done doing that, I send them off to the disk.
Your whole confidentiality and integrity is based on encryption.
Yes. Well, as far as devices go, as long as the primary partition has control of all the devices, you'll have to rely on crypto tunneling for the devices. The rest of it, I mean, what I really meant by integrity and confidentiality is sort of computations that go on in memory. While my partition is running, no other partition can come in and modify its state in memory.
Okay, I think we need to take this online because it should take a break. Offline. It should take a break.
Okay.
I'll do put my hand up. Seems to me you have this version 1, which depends, as you said, on log-board running into primary partition. Presumably, the things that are required of log-board to maintain the operation hypervisor are eventually going to go into public domain somewhere, or at least that will be a nice clean interface.
Yeah, I think I would agree with the latter rather than the former.
So why not write a little operating system that just does everything you need to keep hypervisor running, like scheduling, memory management, device management, and then you've always got a version 2 hypervisor. This is the trusted code, of course.
Yes, that's possible, and I mean, that's possible, but it's currently not the plan. I mean, it makes perfect sense to me. It makes perfect sense to me, and I mean, you would certainly get benefits out of having a small operating system rather than a gigantic operating system be this primary partition. So, I mean, whether that will get built or not, and whether it will get built by Microsoft or not, is sort of subject to, well, business considerations and whether people can think they can make money on that. And anyway, yes, I think it's a good idea, but it's not the plan currently.